we have studied that current is associated with flow. We have seen that whenever there is a flow of electrons, there is also a flow of current. And we have considered their directions to be opposite to one another. Now tell me that whenever there is a flow, shouldn't there be a starting point and an ending point? For example, if we consider a waterfall as has been shown in the picture, over here we can say that the waterfall starts at this position and ends at this position. So clearly there is a starting point and an ending point for the flow of the waterfall. So, and as you can see in this picture, water is flowing from a high level to a low level. So there is a definite direction of flow which has a starting point as well as an ending point. Now consider another example. Over here, two vessels of water has been considered. Now as you can see, in the first vessel, initially the level of water is much more than that of the second vessel. Now once they are connected, water flows from the first vessel to the second vessel until the water level in both becomes equal. Now why is this happening? We can say that in the vessel which has a greater amount of water, it has the capability to transfer water from itself to the other vessel. In other words, we can say that the vessel containing more water can actually work to transfer the water from itself to the next vessel. Similarly, if we consider two vessels again, whose difference in water levels is not as much as in the previous case, we will see that even in this case, water flows but to a less extent. So even in this case, we can say that the amount of water that is contained in the first vessel is being transferred to the second vessel. So the first vessel has a capability to do work to transfer this water, but it is not equal to the amount of work which was being done in the previous case. Now consider this scenario where the water level is equal in both the vessels. Now even when they are connected, you will find that there is no transfer or no movement of water. So what can we say? We can say that the vessels over here have no capability to do work in order to transfer the water from one vessel to another. So we can actually derive a similar conclusion in case of charges. Now before we do so, consider another example. Now let's say that it is a very hot Sunday afternoon. So what usually happens on an afternoon that is quite hot and sultry? You would normally feel lazy, right? And you would normally not feel like doing any work. You would probably just want to lie around or sit in the sofa in a lazy manner. But let us say that your friends have invited you out for a picnic. So the moment you hear the word picnic, you are full of enthusiasm and you actually want to do more work once you reach the picnic spot. So you are in a highly energized state, unlike on a lazy afternoon where you had nothing to do and you were in a lazy state. So we can actually derive these examples and apply them in case of charges. The example of the water flowing from one vessel to another, as well as the example of the lazy child, as well as child in the picnic. So normally what happens? You would obviously prefer to lie around in the sofa doing nothing because obviously you are at rest at that point of time. So in that case, you are said to be at a low potential, or your potential to do work is less. Similarly, as we saw in the case of the water vessels, the water which in the first vessel, which had more water in it, had the capability or the potential to transfer the water from itself to the next vessel which had a less amount of water. So consider two bodies over here. One of the bodies is negatively charged and the other body is positively charged. So what does this mean? This means that the negative body has an excess of electrons and the positive body has a deficit of electrons. So we have learned that whenever these two bodies are connected, electrons flow from the negatively charged body to the positively charged body. But in a day when the electrons had not yet been discovered, do you know what was considered? It was considered that the positive charges flow from the positive body to the negative body when they are connected. Conventionally, it was considered that the positive body is at a high potential, because then when electrons were not discovered, it was considered that charges flow from the positive body to the negative body. So likewise, since the positive charges were considered to be flowing from the positive to the negative body, and the positive body was considered to be at a higher potential, similarly, the negative body was considered to be at a low potential. So it was thus discovered and thus stated that the flow of current is from high potential to low potential. So as we can see, the direction of current was considered to be flowing from the positive body to the negative body. And it was also conventionally considered that this is at a high potential and this is at a low potential, because the charges were considered to be flowing from this direction to that direction in a day when electrons had not been discovered. Now, after the discovery of electrons, certain things changed. It was known that it is not the positive charges that are flowing. On the other hand, electrons are the bodies that are flowing. And we have seen that since this is negatively charged, it contains an excess of electrons. And since this is positively charged, it contains a deficit of electrons. So what was found out? It was found out that the electrons flow from the negatively charged body to the positively charged body. But earlier, the convention that had already been considered stated that current was flowing from the positively charged body to the negatively charged body. That is, from a high potential to a low potential. So this fact was not changed. The fact that this body is at a high potential and this body is at a low potential remain the same, because otherwise it would have become very confusing after the discovery of electrons. So what was considered as the rule? It was finally considered that even though the flow of electrons is in this direction, the direction of flow of conventional current is the exact opposite, that is, in this direction. So electrons are flowing from a low potential to high potential, and current, in keeping with the earlier convention, flowed from high potential to low potential. That is, from the positively charged body to the negatively charged body. And this was known as the flow of conventional current, or simply current. Now we are going to talk about a certain concept which is known as potential energy. Now, before we consider potential energy in the case of charges, let us revisit the concept of gravitational potential energy. Now, in this case, we have a pretty tall building. Now, let's say you are taking a ball and moving up the building and reaching the roof. So, when you are moving up the building, you are basically doing work against gravity in order to move the ball from the ground to the top of the roof. You are basically doing work in order to move the ball from the bottom to the top of the building. Now, when you reach the top of the building, you release the ball. What will you find? You will find that this ball is moving from the top of the building and falling down back to the ground. So what does this mean? This means that even the ball is moving from a higher potential to a lower potential. As you can see in this case, the top of the building has a greater gravitational potential, and the bottom, that is the bottom of the building or the ground, has low or zero gravitational potential. So this is why when you throw the ball off the top of the building, it falls down. Now, if you recall, I mentioned that when you are moving the ball up against gravity, you are doing a certain amount of work to move it against gravity. So this amount of work that you're doing on the ball is getting stored as the potential energy of the ball. Now, a similar thing happens in the case of charges as well. Let us consider that a positive charge has been kept inside an electric field. Now, as you can see, this plate contains a deficit of electrons, so it is positively charged. And this plate has an excess of electrons, and thus it is negatively charged. So when the charge, the positive charge, is kept near the negative plate, there is an attractive force between these unlike charges. Now, I want to move this charge from the negative plate to the positive plate. And as you can see, the direction of the electric field lines is from the positive plate to the negative plate. So when I want to move the positive charge towards the positive plate, there will be a certain amount of repulsion taking place. Why? Because this charge and these charges are like one another, and we know that like charges repel. So we have to do a certain amount of work on this charge in order to move it against a repulsive force, or in this case, against the electric field, which is in this direction. So we have to move the positive charge against the electric field. So in this case, there will be a change in potential of the charge, just like there was a change in potential of the ball when it was carried against gravity. In this case, it is being carried against the electric field. So there will be a change in potential of the charge due to the work that is being done, and it will depend on the work that is being done. You will notice that if I move this charge from the negative plate to the positive plate, I cannot just leave it there. Why? Because the moment I leave the charge, this charge will immediately fall back down to the negative plate because of the repulsive forces of the positive plate. So if I have to hold the charge near the positive plate, I have to do a certain amount of work because I am doing it against the electric field, and there is constant repulsion by this electric field. So work needs to be done to hold the charge near the positive charges, and this work done is translated into the potential energy of this positive charge. So now let us find out how we can define potential energy. The potential energy, or the electric potential energy, since we are considering charges, the potential energy which a charged object has when placed inside an electric field, that is, when the charge is placed in an electric field around other charges, as we saw in the previous case where the charge was kept around positive charges, is known as the electric potential energy. So how can we define the electric potential energy mathematically? Mathematically, it is equivalent to the work done in order to move a positive charge against an electric field. So the amount of work that is being done to move the positive charge against the electric field is getting stored as the potential energy of the charge in the electric field. So now we talk about a slightly different but related concept, that is the electric potential difference. So we just found out what the potential energy of a charge is. Now how can we define the electric potential difference? The electric potential difference between any 2 points in the electric field is the difference in the electric potential energy between the 2 points for a unit positive charge. So let us say that when we were moving the charge from the negative plate to the positive plate, these 2 points will have different amount of potential energy. Why? Because obviously work needed to be done in order to move it from the negative plate to the positive plate against the electric field. So if we consider a unit positive charge in that case, then the difference in the potential energy between 2 points in the electric field would give us the electric potential difference. So mathematically we can define the potential difference as the difference in electric potential energy divided by the amount of charge on the body we are considering. So let us say we have 2 points inside an electric field, and we have to carry a charge, that is this positive charge, from B to A. So when we are carrying the charge from B to A, we have to do a certain amount of work. So this amount of work will determine the potential energy. And if we consider this work per unit charge, in that case, if we consider unit charge, it will give us the potential difference. Thus, if we are moving a charge from B to A, it is getting stored as the electric potential energy of the charge, and we are finding out the electric potential energy or the difference in electric potential energy in between those points for every magnitude of the charge. And since we have studied that the work that is being done is getting stored as the electric potential energy, we can say that the potential difference in between points B and A is nothing but the work done in order to move the charge from B to A per unit of the charge. So as you can see, potential difference between 2 points is the work done per unit positive charge in carrying it from one point to the other. So we have defined that V is equal to W, that is work done, divided by Q, that is the amount of charge. Now we have seen that the unit for work done, which is getting transformed into the potential energy, is joule, because it is a form of energy and energy is measured in joules. The unit for charge is coulomb, and thus the unit for volt will be joule per coulomb. Joule per coulomb is also known as volt. So if we have done 1 joule work in moving a unit positive charge from one point to another, we can say that the potential difference between those 2 points will be 1 volt. Now we consider another interesting concept. We define the potential difference in between 2 points. Now what if we have been asked to find out the potential at just one particular point? In order to do so, an assumption is made. What is the assumption? The assumption is that any point at infinity is at zero potential. Why? Because it is considered that at infinity there are no charges present. And since there are no charges present, there will be no force on any charge kept at infinity. So this is the reason why infinity is considered to be at zero potential. So now how can we define the potential at a single point? The potential at a point can be defined as the amount of work done in bringing a unit positive charge from infinity to the point under consideration. Why? Because we have considered that infinity is at zero potential. So if we have to find out the potential at any given point in an electric field, we simply bring a charge, that is a unit positive charge, from infinity to that point. And the amount of work done will give us the potential at that particular point in the electric field. So when the charge being considered is 1 coulomb, because we are considering a unit positive charge, and when the work done to bring the charge from infinity to that particular point in the electric field is 1 joule, that is 1 joule of work is being done in order to bring 1 coulomb of charge from infinity to the point in the electric field. Under such circumstances, the electric potential at that point is 1 volt. So over here, the unit positive charge is being brought from infinity to a point P inside an electric field. Under the circumstance, if 1 joule of work is being done in order to bring 1 coulomb of charge from infinity to point P, we can say that the potential at point P will be 1 volt. So we have studied about what potential difference is. Usually in day-to-day life, potential difference is also known by various other names. It is also known as voltage or the voltage difference, and it is also called electric potential difference. All these terms mean one and the same thing, as you can see over here. So if we take a quick recap, what did we learn so far? We learned that there is always a direction attached to the flow of current. That is, it has a start point and an end point. Before the discovery of electrons, it was considered that positive charges move from the positively charged body to the negatively charged body. And that is why it was considered that the positively charged body is at a high potential and the negatively charged body is at a low potential. But after the discovery of electrons, it was found out that positive charges are not moving. It is the negative charges that actually move from the negatively charged body to the positively charged body. That was the direction of flow of electrons. But since the convention had already been earlier considered, to avoid confusion, it was considered that the flow of conventional current is from positive to negative, that is from a high potential to a low potential, and the direction of flow of electrons was from negative to positive, that is from low potential to high potential. We also found out the definitions and meanings of certain concepts relating to potential. We found out that when a charge is moved against an electric field, that is from negative to positive, if we move a positive charge, we have to do a certain amount of work. This work gets stored as the electric potential energy of the charge. If we consider the electric potential energy per unit charge, it gives us the potential difference between any 2 points in the electric field. We also learned how to find out the potential at any given point in the electric field. That is, if we bring a unit positive charge from infinity to a particular point in the electric field, and if the work done in bringing the charge is 1 joule, we found that the potential at that point can be considered as 1 volt. Why? Because the definition for volt or the electric potential difference was given as the work done divided by the charge that is being considered.